Hello guys, welcome back to Techdose, and in this video we will see the sieve of eratosthenes algorithm, which is used to find all the prime numbers till a given number n. So let us look at the problem statement. In this problem, let us say we are required to find all the prime numbers till a prime number n, and let's say n is 19. Then how can we find it by using this algorithm? We will create an array which I will call as the prime array, and this we will call as sieve as well. So why do we call it a sieve? We will understand it later. The size of our array will be n plus 1. So you can see that n was 19 and this array size is 19 plus 1, which is 20. Now we don't care about this 0 and 1 since our prime number will start from 2. So this entire array has been assigned as true, which indicates that all of these numbers are prime numbers. Now we will make a list of prime numbers and we will insert in this list each element one by one. So we will start iterating from this number 2. So this number 2 is true. Therefore we will insert this in our list of prime numbers and we will say that this is a prime number. Okay. Once we insert this, then we will mark all the multiples of this 2 as non-prime numbers. So what will be the multiples of 2 which are non-primes? It will be 4, 6, 8, 10, 12, 14, 16 and 18. These are all the non-prime numbers. Okay. Now we will move on to the next number. You can see that 3 is also true. That means 3 is also a prime number. Now we will need to mark all these multiples of 3 as non-prime numbers. So multiple of 3 is 6, already marked. 9. Then we have 12 already marked. 15. Then we have 18 already marked. Okay. Now we move to 4. 4 is a non-prime number, so we'll move to 5. 5 is a prime number, so we'll include it in the list of prime numbers, and then we will mark all the multiples of 5. So 10 has been marked and 15 has been marked, and there is no other multiple of 5. We move to 6. 6 is a non-prime number. Similarly, we move to 7. 7 is a prime number. We will mark all the multiples of 7. 14 is marked and there is no other multiple of 7. Now 8, 9, 10 are non-prime numbers, so we move to 11 directly after comparing these numbers. So 11 is a prime number, include it in the list of prime numbers, and then there is no multiple of 11. So actually what we can do is we just need to move to just element n by 2 less than equals to n by 2. Why? Because after n by 2 there will be no multiple of the prime number. So suppose we have here 19 elements. Okay, so what will be 19 by 2? It will be nothing but 9.5, and since we are dividing it by integers, so it will be 9. So we just need to move to this 9 and no further elements. Okay, so when we are done at this location 9, then all these numbers are marked and the non-marked numbers are actually the prime numbers. So from here on we can just traverse this and include the non-marked elements as our prime number. So 11, 13 and 17 along with 19 is included, and this is the list of prime numbers. So I hope you got the simple idea about the sieve of eratosthenes. So this is the code for that simple implementation. We have I equals to 2 to n by 2, and I already explained why we will go to n by 2 only. Then if the prime at I is true, that means the current number is a prime number, then we will make all the multiples of that prime number as false, because all the multiples will be having a factor as this prime number itself, and so they will be non-prime. So this is a simple implementation. Actually we can improve the time complexity of this simple implementation. Now let us see how can we improve this algorithm. If we are given a number n, then if it is a non-prime number, then there will exist at least two factors of this number n, where x is less than equals to square root of n and y is greater than equals to square root of n. It is guaranteed. If n is a non-prime number, then this is guaranteed. Okay, so how will this help in improving our time complexity? Actually what we were doing is we were searching from I equals to 2 to n by 2, and what we were doing is we were just marking all the multiples of these prime numbers. Okay, so what we need to do is we don't need to even traverse till n by 2, but only to square root of n. Why? Because if a number n is non-prime, then it will have at least one factor which is less than equals to square root of n. So we just need to check till square root of n, and if it can divide this n, then this n will not be a prime number. And if we check till square root of n and there is no factor of n, then we can say by guarantee that this n is a prime number. Okay, so this is an optimization for this loop. It will be till square root of n. So I hope you understood the first optimization. There is yet another optimization which is related to this first property which we saw. Elements need to be marked from I square. Here you can see that when we were marking the multiples of this prime number as non-prime, then if we are at a number I, then we were storing it as a prime number. Okay, and from 2i till we reach n, we were marking all the multiples of this I, 2i, 3i, 4i as non-prime numbers. Okay, so I have already shown you how we were doing it. We were just making it false. What we can do is we can optimize it and we can start directly from I square. That is, if I is a prime number, then we won't start from 2i. We start marking from I into I, that is from I square itself. So this is another optimization. And why this will work? Let me show you an example. This is an example. Let's say you are at this 5, your I equals to 5, and you found that this is a prime number. Then when you are at 5, then all the multiples of these 2 and 3 which were already found as prime numbers are marked, and they are marked in red and green. Multiples of 2 are marked in red and multiples of 3 are marked in green. If you start marking with like 5 into 2 like we did previously from 2i, then you can see that 10 is already covered, then you see 15 is already covered, 20 is already marked, and so on. Okay, so it is guaranteed that if you are at a number I, then all the numbers till I square will be marked by the previous prime numbers. So why this is always true? Because if you consider this 5, then 5 into 2 is 10, but 10 has already been covered. Why? Because 10 is a multiple of 2. So all the multiples of 2 have already been covered, because this is nothing but multiplying 2 5 times. 2 into 5 is nothing but 10. So when we have already marked 2 into 5, so there is no need for marking this 5 into 2. This is just a waste of time. This is just multiplying duplicates. Similarly, when you have this 3, then we have already covered 3 into 5, which is 15. Okay, so you can see that 15 has already been marked. Now there is no need to mark this 5 into 3, which is 15 only. Okay, so these duplicate markings are removed, and so we will start with I square. So this is yet another optimization, that j will not start from 2i, but it will start from I square. This is the optimized code for the sieve of eratosthenes. Here I will start from 2 and we'll run till square root of n, and if we find a prime number, then we will mark all the multiples of this prime number as non-prime, and we will start with I square and we will move by I only. Okay, so this step is same, but this is different. And why it is called a sieve? Because we are actually maintaining an array. We are keeping track of all the numbers which are prime and which are non-prime. So this is just like a sieve which is used to filter out the gravels and pebbles from dust. Okay, so similarly this array is acting like a sieve. It is actually filtering out the prime numbers from the non-prime numbers. That's why this algorithm is known as sieve of eratosthenes. Now what will be the time complexity of this algorithm? Actually, for this first prime number 2, we will have to mark n by 2 number of elements in our sieve. For the second prime number 3, we will have to mark n by 3 elements in our sieve. And similarly for 5, 7 and so on till p, which is the largest prime number which is less than equals to n. So for this we will have to mark n by p number of elements. Now if we take n as common, then our series will be 1 by 2 plus 1 by 3 and so on till 1 by p. Now this is a harmonic progression of sum of primes, and it has been proved that it will come out to be log n. So this n was common, and therefore the time complexity will come out to be n log n. So I will put the explanation of this log n in the description below. You can check it out. I hope you understood the sieve of eratosthenes. The code will be present in the description below, so do check it out. If you have any type of doubt, then feel free to comment below and I'll try to help you as soon as possible. Like and share our video and subscribe to our channel in order to watch more of these programming videos. See you in our next video. Thank you.